today's speaker is Basile Gallet, who is a researcher at CEA in Saclay, south of Paris. So before getting this position, Basile was a PhD student at the École Normale Supérieure in Paris, and he got his PhD degree in 2011. He has done 2 postdocs, one at Scripps in 2012, and the other at Orsay in 2013. And he has won several prizes, including one from the Euromec Society in 2019 as a Young Scientist Award. So his work focuses on geophysical fluid dynamics that he tackles with numerical simulations, experiments, and theory. And he has worked so far on fundamental turbulence and MHD, turbulent convection. And today, I believe he's going to talk about turbulence in the atmosphere and the ocean. So, Basile.
So, thank you very much for the kind introduction and invitation. It's a great pleasure to be giving this webinar. And as you said, I usually work in turbulence. I'm an expert in convective turbulence and rotating turbulence and MHD turbulence. And at some point, I thought, well, is this knowledge of turbulence of any use to climate dynamics? Can I be used there? And so I got in touch with Raf Ferrari, who's part of the Climate Modeling Alliance. And within this collaboration, the goal is to try to develop a new climate model that has additional features, including new parameterizations that hopefully are more physically based than what is currently used. And so I saw this development of new parameterizations as a great motivation to go back to the fundamental flows that you find in the climate system and try to do some turbulence research related to that and try to help in that context. Okay, so the basic problem is the following. You have a planet here that receives heat from a nearby star, and it's receiving more heat at the equator than at the poles. Okay, and without the fluid envelopes of the planet, you would have a huge temperature difference between the equator and the poles. But what happens is that the ocean and the atmosphere are going to be set in turbulent motion, and this turbulent flow is going to efficiently transport the heat from the equator to the poles, thus reducing the temperature difference between the two. And so the key point, the key thing to understand is how to parameterize that transport so that you can compute the resulting temperature profile on the planets. Okay, so if you consider the atmosphere on Earth, again, it's receiving more heat at the equator than at the poles, so you need to move that heat poleward. And what happens is that you have some kind of convection, but also because you have this meridional temperature gradient here, you're going to have some jets flowing in the zonal direction that are in thermal wind balance with the meridional temperature gradient. And I will explain what that is. And that could be a perfectly valid equilibrium state, except that it is unstable. And it is subject to the baroclinic instability, which is an instability that leads to eddies and turbulence here, which again will greatly enhance the heat transport between the equator and the poles, and thus reduce the temperature difference between the equator and the poles. Okay, here is an animation of that if you consider a quite simple atmospheric model. What you can see here is the surface temperature as a function of longitude and latitude. So here is the equator, it's warm, and here are the poles, and you can see the zonally averaged temperature profile here. Okay, and in thermal wind balance with this meridional gradient here is a zonal wind. So you can see the wind here in the zonal direction. It's sheared in the vertical direction. And this vertical shear is what thermal wind balance tells you. So again, that's a valid solution to the problem, but you'll see that it's unstable when I play the animation. And you can see now that a wave is going to develop, and then turbulence will follow. And if you see at that temperature difference here between the equator and the poles, it's going to be reduced as a function of time, because that turbulence is transporting heat poleward. Okay, here is another movie, but now that's data. That's from a reanalysis. I got that on John Marshall's website. You're looking at the potential temperature. Fortunately, I don't have a color scale, but you can guess that red is warmer than blue. And if I play that animation, what you can see are intrusion of warm fluid that are moving northward. And here you can see some cool fluid that's moving southward. So here there's a correlation between the meridional velocity and the temperature, which means that there is a turbulent heat flux towards the poles here. Okay, you get the same picture in the ocean, and I'll be focusing here on the Antarctic circumpolar current, which flows around Antarctica here. So if you zoom in on that region, you have a temperature gradient again between Antarctica and the more equatorward latitudes. And associated with this temperature difference, again, there is a flow, a current, which is in thermal wind balance. And again, this flow is unstable because of the same baroclinic instability. It evolves into turbulence. And you can see here that there are some turbulent eddies. And what's represented here is the surface velocity from the Southern Ocean State Estimate. It's a reanalysis. And if you unfold that picture, you can see what it looks like as a function of longitude and latitude. And you can see you can kind of get some jet-like features coexisting with some isolated vortices here that you can see. Okay, so this turbulent heat transfer, it's not going to be resolved in the ocean part of a climate model. So it has to be parameterized using ad hoc coefficients, some kind of turbulent diffusivities, if you wish, that have to be tuned to produce the expected behavior. So, there's as much physics as we can in these parameterizations, but they're not always fully physically motivated, sometimes poorly controlled. And so it's this order one phenomenon that we need to understand physically to make accurate predictions in that context. And yet, if you consider even the simplest settings of baroclinic turbulence, and I will show you what that is, that's the two-layer quasi-geostrophic model, which I will introduce in a few slides. Well, even for that simple model, we do not understand the scaling behavior of the eddy diffusivity. So I'll be asking questions such as what physical processes set the eddy diffusivity? What is the scaling behavior of that diffusivity with respect to the external parameters of the problem? And then once I've understood that scaling behavior, can I use it as a parameterization? Can I use that diffusivity as a closure when the system is subject to some large-scale forcing, which is inhomogeneous in the meridional direction, like you would have on a planet? Okay, so there's going to be three parts, but really there's one long part here where I will introduce the two-layer quasi-geostrophic model, focusing on uniform planetary vorticity for the first part. I will derive a scaling theory based on a homogeneous model, and I will show you that the scaling theory can be used as a parameterization when the system is forced by some inhomogeneous driving the meridional direction. So that's a nice fundamental fluid dynamics problem, but it's lacking important ingredients of planetary dynamics, especially a planetary curvature, which I will include in the second part of the talk through the beta plane approximation. I will show you what that is. And I will augment the scaling theory to include that effect and show you its skill as a parameterization again. And finally, a few conclusions and perspectives on what we need to do if we want to have a fully efficient parameterization for a true climate model. Okay, so two-layer quasi-geostrophy. Here is the model. You can see it's quite simple. It's two layers of immiscible fluid that are treated in the shallow water approximation, meaning that inside each fluid layer, the velocity field is independent of the vertical coordinate. These two layers are rapidly rotating around the vertical axis and subject to the gravity. And this fluid here in the bottom layer, it's heavier than the layer on top. And in fact, we'll consider that it's heavier because it's cooler fluid here and warmer fluid on top. Now you could describe this system by considering two stream functions, psi1 and psi2, inside the two layers, layer 1 and layer 2. But it also proves insightful to change variables and use instead this barotropic stream function psi, which is just the average of the two stream functions. And this is going to be the part of the flow that is invariant in the vertical direction, meaning when you average over the two layers. And the associated barotropic flow will correspond to most of the kinetic energy in the system. You can form another variable, which is the difference between the two stream functions. Now, what's nice is that in quasi-geostrophy, or in geostrophy, the stream function is directly related to the height of the fluid layer, meaning that the difference in stream functions is directly related to the height of that interface here. But if you think of the height of that interface, it's also directly related to the vertically average temperature of a local fluid column. Okay, consider that position, for instance, there is more dense fluid here, more cold fluid. So if I average the temperature over the vertical, that fluid column is colder than when the interface is at rest because I have more cold fluid here. In this part here, I have more light fluid, so the vertically average temperature is higher. So on vertical average, you can say that here you have warm fluid, here you have cool fluid. So now again, this baroclinic stream function tau, it directly encodes the position of the interface, which is also the vertically average temperature of the system. So we'll just, for that reason, we will directly refer to tau as the temperature in that system, even though it has units of a stream function. Okay, so vertically average flow and temperature in that system using that Chandra variable. Okay, the equations of motion that follow from the conservation of potential vorticity, which you can understand easily if you start by forgetting about these terms here, in which case Q1 is just the vertical vorticity in layer 1, and Q2 is vertical vorticity in layer 2. These equations here are then just the material conservation of the vertical vorticity. This is the 2D Navier-Stokes equation in layer 1 and 2D Navier-Stokes equation in layer 2. Well, that would be boring because then the two layers would be uncoupled. But then there are these two terms here that couple the motion between the two layers. And the origin of these coupling terms, you can see that they're proportional to the difference in stream function, so to the height of the interface. And what happens is that if you move the interface, then you're going to compress one fluid column here and stretch the fluid column here. And because of conservation of angular momentum, this will directly impact the velocity inside both layers. So that's how the two layers are coupled. It's through the motion of the interface and the conservation of angular momentum. And these two coupling terms are now coupling the 2D Navier-Stokes equations. Now, there are also damping terms on the right-hand side. You have viscous damping, and in fact, I'll be using hyperviscous dissipation, but it doesn't matter. And there is bottom friction in the lower layer that's here to mimic the friction that you would have on the roughness elements at the bottom of the ocean. Okay, so this is the two-layer QG model. And then we're going to consider a simple base state for that system, which is the following. It's a base state in which you have a uniform zonal flow inside the two layers with opposite directions in the two layers. So you can see in this two-layer framework, this is the equivalent of a vertically sheared zonal flow. Okay, you have zonal flow with a difference in the vertical. Now, associated with this vertically sheared zonal flow, there will be a tilt in the interface here, and that's the equivalent of thermal wind balance in this two-layer model. Okay, so now I can explain to you what thermal wind balance is. Well, basically, you can think that you start with a flat interface and you want to have that zonal flow here. Well, that's not going to work because of the Coriolis force and omega, these flows will want to turn right as they move. So fluid would pack up on that side, and here fluid will pack up on that side until you have a strong enough pressure gradient to fight the Coriolis force and to allow the fluid to go straight again. That means that that leads to a tilted interface. And the tilt of the interface, the slope here, is directly proportional to the velocity u inside the two layers. Okay, but if you have a tilt of the interface, you also have a gradient in the meridional direction of vertically average temperature. On this side of the domain, the fluid is colder on vertical average because I have more cold fluid here. I have more warm fluid. The fluid is lighter on vertical average, which means I have a temperature gradient in the meridional direction in this system. So this is the base state of the system. And this base state is going to be unstable and subject to the baroclinic instability. So this tilted interface, it's associated with potential energy because you would have less gravitational energy if the interface were flat. And what the system is going to do is that it's going to try to release that potential energy by producing turbulence through the baroclinic instability, hoping to flatten that interface. Okay, so you can study that dynamics using, again, two stream functions, which are now the departure stream functions from that base state here. Okay, and same thing, you can then go from the two departure stream functions to the departure in barotropic stream function, the vertically average flow, and the temperature field. Okay, so here is what it looks like, and I'll just add a few precisions on the friction force at the bottom. We'll be considering two cases. Either linear bottom drag, which is what you get from a nice Ekman layer on a flat bottom boundary. You can do the analysis and you get linear drag at the bottom. But the bottom of the ocean is rough, and probably a better parameterization of the effect of that bottom boundary is a quadratic bottom drag due to the turbulent drag on the topography features at the bottom of the ocean. So we'll be considering these two possibilities, these two forms of the drag coefficient. Well, regardless of that form, when the drag is low, the flow looks something like that. I'm showing here the barotropic vorticity, which contains most of the kinetic energy of the flow. And here is the temperature field, which is also the baroclinic stream function. And here you can see the animation. And I'd like to convince you here that this flow looks very much like a vortex gas, a gas of isolated vortices here with not much vorticity in between the vortices. By contrast, if you look at the temperature field, well, of course, you can see the vortices, but that's a small fraction of the total thing. And you have significant temperature between the vortex cores. Okay, so what this turbulence is doing, again, is that it's trying to release potential energy from the system. So the meridional velocity, which is the vertical component here on this graph of the velocity field, is trying to move the warm stuff northward and to move the cold stuff southward. Okay, so there is a correlation between the vertical velocity here, the y component of the velocity field, and the temperature field, which you can see here, which means that there is a net meridional heat flux V times tau, meridional velocity times temperature in the system. And we would like to, this is exactly the quantity that we would like to know if we're to deduce a parameterization. That's the quantity of interest. So instead of that, we'll be using an eddy diffusivity, that diffusivity being the heat flux divided by the background temperature gradient, which I told you, because of thermal wind balance, is directly proportional to U. Okay, so diffusivity is just heat flux divided by gradient. And that's the quantity of interest for a parameterization. Another quantity that proves very useful is the mixing length L, defined as the root mean square temperature fluctuations divided by the background temperature fluctuations, the background temperature gradient, excuse me. The idea is the following. If you have a fluid column that starts with its initial temperature, inside this background gradient, well, you can idealize the turbulence picture by thinking, well, it's going to travel over a mean-free path that's typically L, and that's this mixing length, before colliding with the turbulent environment and relaxing to the local value of the background temperature. Well, during these events, you can see that the typical root mean square temperature fluctuations that arise are given by the background gradient U times L, the mixing length. So that explains that definition here. Okay, so we'd like to understand the behavior of these two quantities. And of course, we're going to ask these questions in a dimensionless form to make things simpler. So the control parameter of that system, I should have said, that's the deformation radius here, which a length scale that arises in the coupling term between the two layers. So it's a length scale that depends on the density difference here and the rotation and G. And then there is the value of the shear flow, the magnitude U here of this velocity in the two layers. Okay. So we're going to non-dimensionalize these diffusivity D and this mixing length L using U and lambda, which are the two parameters of that system. And we'd like to understand the behavior of the diffusivity and mixing length as a function of the drag coefficient, which again, we make dimensionless using the two parameters of the system, U and lambda. Okay, so the drag coefficients have different dimensions depending on whether it's linear drag or bottom drag. So this is linear dimensionless drag coefficient, kappa star, and here the quadratic drag coefficient in dimensionless form, mu star. Okay, so we're asking the dependence of these guys as a function of those guys, and of course we're not the first ones to wonder about that behavior. And in fact, Thompson and Young did a fairly extensive numerical study of the system, and here is what they found. You can see the turbulent diffusivity in dimensionless form as a function of the dimensionless drag coefficient. And you can see that if you forget about finite size effects, which are all these points, well, then all the points obtained for various values of the size of the domain, etc., they fall onto this master curve here, which is the dashed dotted line here, which has an exponential behavior in inverse drag coefficient. Now, if you're into scaling analysis, that may come as a surprise to you. We're used to scaling laws that are typically power laws. Worst case scenario, it's a power law times a log correction, but an exponential is kind of pushing it really. So we'd like to understand that behavior, which they obtained through a best fit to their data. Then more recently, Cheng and Held considered quadratic drag instead of linear drag. And they showed that it changes the picture quite dramatically because this very high sensitivity on linear drag is transformed into a power law dependence on the quadratic drag coefficient. Okay, so instead of the exponential, you get nice power laws with exponents that they diagnosed, obtained 0.58 here, minus 1.24, which are somewhat different from the standard cascade arguments that you can use. And so we're wondering, well, can we provide a unified explanation to both the exponential scaling in Thompson and Young and the power law behavior in Cheng and Held for quadratic drag? Okay, and so we followed the intuition of Thompson and Young, who said very clearly in their paper that they believe that the flow may be better described in physical space than in spectral space. Again, that's a bit of a surprise if you're used to turbulent dynamics, because, following Kolmogorov, we think that it's a great idea to just describe the flow in spectral space. But here they're saying, well, maybe not, because you have these coherent structures, and the flow truly looks like a gas of isolated vortices, and maybe you should really consider these coherent features. So that's what we did. We considered a gas of vortices very idealized. You see, they have either two values of the circulation for these vortices, either plus gamma or minus gamma. They have a core radius, which is given by the Rossby deformation radius, lambda, which is the injection scale of baroclinic instability. There is an intervortex distance here, LIV, inside this model, a typical value. And as a consequence of mutual induction between these point vortices, well, the vortex cores will move at a typical velocity, capital V here, which is circulation gamma divided by intervortex distance, maybe 2 pi times intervortex distance. Okay, so with this vortex gas picture, it looks like we've actually made things worse. We have even more parameters to understand. We have the diffusivity, we have the mixing length again, but now we also have the intervortex distance, and we have this velocity V at which the vortex cores move, or equivalently the circulation gamma, which is LIV times V, and a drag coefficient kappa or mu. So these are 5 quantities. If we want to have a fully closed scaling theory, we need 4 relations between these quantities, and these relations will be inside red boxes. Because the first thing to understand is how is this vortex gas going to transport heat? Well, you can understand that process quite simply if you go to very large scales, much larger than the deformation radius, for which the temperature equation, it reduces to an advection diffusion equation for the temperature field with a source term U times V, which is just the fact that the meridional velocity V is going to distort the background gradient U. Okay, so the turbulent velocity distorts the background gradient, and that leads to a departure here, a temperature anomaly tau. So now, if you want to understand how the vortex gas is going to transport heat, you can just consider a dipole of vortices, two vortices inside the gas. Well, around this dipole of vortices, you can see that the meridional velocity is going to be positive between the two vortices and negative on both sides of the dipole. If U is positive, it means that U times V is a positive term, so it's a heat source between the vortices, and I have heat sinks on both sides of the dipole. So these sources and sinks, they're directly correlated with the sign of V of the meridional velocity, which means that V times tau is positive here, and it's also positive on both sides of the dipole, okay? So I will have a net heat flux V times tau in this configuration. This does not depend on the sign of the vortices. In fact, I can switch their signs, in which case I have negative V here, a heat sink here, and two heat sources on both sides of the dipole. So regardless of the orientation of that dipole, I would get a positive heat flux V tau in the system. Okay, so you can understand heat transport in this vortex gas by considering just two vortices like that. And in fact, what I've done here is that I've integrated this advection diffusion equation with a source term over the typical process that takes place inside the vortex gas, which is that two vortices will mutually advect over a distance that's comparable to the intervortex distance, after which they pair up with other vortices inside the gas. Okay, so here is a typical simulation. You can see these two, the vorticity here. You can see the temperature, and you can see the related heat flux here. So you can see that indeed you have positive temperature in the middle, negative temperature on both sides. There is a net heat flux associated with this, and you can repeat that simulation, changing the distance between the vortices, and get the scaling behavior for the mixing length and the heat flux in these simple events of dipolar heat transport. And you get that the mixing length is directly proportional to the intervortex distance. You get that the heat flux, so the diffusivity, is proportional to the intervortex distance times the velocity at which the two vortex core move because of mutual induction. Okay, so I have two relations already, and I need four, I told you. The third relation will sound obvious to the experts in turbulent convection, for instance, and I've called it the slantwise freefall argument. And the idea is the following. You can consider a fluid column here that's initially here, and in fact is going to move spontaneously. It's going to fall down this slope here and move in a warmer region. And during this, it's like the free fall in convection, except that now it's falling in a slanted direction. So over this process here, which is one mixing length, I told you can think about that as a mean free path. So this column is going to move without interfering with the other fluid column. That's this very idealized picture, which means that it's going to transfer its potential energy into kinetic energy. And if you equate the two, you get that the typical velocity of that fluid column is just u over lambda, the parameters of the system, and it's proportional to the mixing length L here in that system. And that is the third relation of the scaling theory. And the very last relation is the power integral. At some point, you have to say that the potential energy that is released eventually is going to be dissipated by bottom friction. Now, the energy that is released is just the product of the heat flux by the temperature gradient. If you think about it, it's like Ohm's law maybe. Well, the current would be the heat flux, the voltage would be the temperature difference. If you want the power, you multiply the voltage by the current. If you want the power here, you multiply the flux du by the temperature difference u. Okay, so this is the power that's released, and eventually it's going to be dissipated by the frictional drag acting on the barotropic flow. And this frictional drag, well, it takes a different form depending on whether you have linear bottom friction or quadratic bottom drag. If you have linear bottom friction, it's proportional to the squared barotropic velocity. If it's a quadratic bottom drag, it's proportional to the third moment of the flow. And in fact, the key point here and the key difference between linear and quadratic bottom drag is due to the fact that the velocity moments, they scale differently inside the vortex gas. Okay, so the naive idea would be, well, this u squared is probably the typical v squared, v being the velocity at which the vortex core moves. And this u cubed, it's probably v cubed as well. But that's not quite the case. If you consider a single vortex inside the vortex gas, it occupies a typical region, which is the intervortex distance, before you can sense the next vortex here. And over this region, you can compute u squared, the velocity variance. For that, you're going to be integrating the velocity associated with this point vortex, which is gamma over 2 pi r, and I'm squaring this velocity. Then I have a 2 pi r dr. So I don't get quite v squared, I get v squared times a log term, log of the dimensionless intervortex distance here. And this log term will be crucial in the scaling theory. If I compute the third order velocity moment here, I don't get quite v cubed, I get v cubed multiplied by this dimensionless mixing length here. Okay, so these different velocity moments scale differently. And this last relation where I replace these expressions for the velocity moments are the fourth relation of the scaling theory. Okay, so then you can combine these various relations. Here are the various relations. And you get that the log of the dimensionless mixing length is 1 over the dimensionless drag coefficient, which you can exponentiate. And you get that the diffusivity is indeed some exponential of a constant divided by the drag coefficient, precisely what Thompson and Young diagnosed. You can play the same game with quadratic bottom drag. And of course, now there's a different expression for the power that's dissipated by the drag coefficient. And if you combine that, you get a power law now instead of the exponential with exponents that are very close to the values that were diagnosed by Cheng and Held in their study with quadratic drag. So we get a common scaling theory underpinning the scaling laws that were diagnosed empirically in these two previous studies for linear and quadratic bottom drag. Okay, so we did our own DNS, or numerical simulations of the two-layer model. I did that on a GPU, and you can see here the dimensionless mixing length as a function of the dimensionless drag coefficient, either linear drag or quadratic bottom drag. You can see the data points for the two cases here in blue and red, and you can see the results of the scaling theory here, the exponential behavior for linear drag and the power law behavior for quadratic drag. So as in any scaling theory, of course, there is a fitting parameter, which is just the prefactor here of that power law. And here I have one prefactor and one coefficient inside the exponential. Same thing for the diffusivity. Again, a good agreement with the exponential behavior with that constraint that this guy must be twice the coefficient I got for the mixing length. And that's okay, that works fine. And here I get the power law with an exponent that's quite well captured by the scaling theory. Okay, so that's quite convincing. But now you can ask, well, now that we've understood the behavior of that diffusivity, can I really use that as a parameterization when the system is subject to some inhomogeneous driving? So I'm going back to these equations, these coupled 2D Navier-Stokes equations, but now I'm adding these source terms here on the right-hand side. And I argue that this source term is a meridionally dependent heat flux. So it does depend on the meridional coordinate y, the north-south coordinate. And the reason it's an imposed heat flux is because if you want to form the equation for the barotropic flow, you sum these two equations, and these guys cancel out. If you want the temperature equation, you take the difference of these two equations, and you get twice this guy here, which means that you have this imposed heat flux that forces temperature anomalies in the system. So very much like in a convection problem, now the issue reduces to, we've imposed the heat flux in the system, can we predict the temperature distribution tau bar of y? The over bar being a zonal and time average, but zonal is enough. And the answer is yes, in fact. If you average these two equations over time and in the zonal direction, you get that this imposed heat flux must be transported by the turbulent heat flux, this V times tau. But v times tau locally, we know, due to the homogeneous model, that it's the diffusivity times u, which is the local temperature gradient in the meridional direction, while the prime is a derivative here. And the great thing is that we know d from previous scaling laws, and we got 1 or 2 fitting constants, just the height of these scaling laws. But once you've got them, there's no fitting parameter anymore, and you can compute this tau bar of y by integrating this equation, which is precisely what we did. And you can see the result here for quadratic bottom drag. It's proportional to the square root of the drag coefficient here, and then there is an elliptic integral. That's the shape of the meridional temperature profile. And so I've run the inhomogeneous model numerically, so you can see the temperature field here. It's fully turbulent. It's warmer here and cooler here, of course, due to the source term. And you can average from an equilibrated simulation like that, you can average the profile in the zonal direction. And the profile you get from the DNS is the blue line here. And the theoretical prediction using the scaling theory is the black line here, the dashed line. And again, once you've chosen the 2 fitting constants to match the data of the homogeneous model, then you have no free parameters here. You can play the same game for linear bottom drag. The equation, the solution is a bit more involved. It involves this Lambert function here, but still you can do it. You can solve the problem numerically. You get a turbulent flow again. You can average that in the zonal direction. You get the temperature profile here as a function of the north-south coordinates. That's the DNS in blue. And the prediction, again, is in very good agreement with the numerical data, both in terms of amplitude and in terms of the shape of the temperature profile. Okay, so these are the conclusions of the first part. We've considered the 2-layer quasi-geostrophic model on the F-plane with either linear or quadratic bottom drag. We came up with a simple vortex gas picture from which we could derive a scaling theory that correctly captures the behavior that was diagnosed empirically in 2 different studies for 2 different forms of the bottom drag law, and in good agreement with the data. And once you get these 2 coefficients here, 3 coefficients, or if you add this one, well, then you don't have fitting parameters anymore, and you can use that as a predictive parameterization for the case where the forcing is inhomogeneous in the meridional direction. Okay, so we're quite happy about that, but at this stage, might be a bit of fundamental fluid dynamics because we're missing, of course, some of the key ingredients of planetary dynamics. And there are several, but arguably the most important of those is the planetary curvature, which will impact the structure of the flow and the behavior of the temperature field. And so we will include that planetary curvature now in the framework of the beta plane approximation, which I will explain now. The idea is that you're studying the motion in a plane tangent to the sphere. And the first thing we did, if you do that, when you project the equations of motion onto the local plane, you have to project the rotation of the planet onto the local vertical coordinate. What we said is, well, it's pretty much a constant here, this projection, but that's not quite true. The orientation of the z-axis depends on the latitude here. And so the projection of omega onto z depends on the latitude as well. And you can include that using Taylor expansion and saying that the planetary vorticity is a constant plus a linear term in the y coordinate. Other than that, it's the same problem with the 2 layers, the same base state with a vertically sheared zonal flow and the tilt of the interface that corresponds to a meridional temperature gradient. Including this beta here leads to a 1 new term here in green in the equations. Otherwise, these are the equations we solved before, written in terms of the stream function and potential vorticity. Okay, so here you can see what the effect of beta is going to be. And in fact, that's well known. Peter Rines explained that very nicely. The idea being the following: if you look at the vorticity field here, you can see vortices again as before, but you can also guess that there are some zonal jets in the system, which show very nicely on the zonal velocity here, blue being positive, red being negative as usual. And you can see some well-organized turbulent zonal jets in the system. And Peter Hines explained that indeed, when you include beta, even in a standard 2D Navier-Stokes equation, if you just add this beta term, what it does is that at the end of the inverse energy cascade, beta will channel the kinetic energy into zonal jets like that. And that will be the arrest mechanism of the inverse cascade. And in fact, from that, you can estimate the size of the jet or the spacing between the jets from a scale which is now called Rhines scale, which you build using beta and the root mean square velocity. So here, the Rhines wave number, which is 1 over that scale, is the square root of beta divided by the root mean square velocity. And this beta plane approximation is probably the simplest explanation for the existence of jets on a planet like Jupiter. Okay, beta is very important if you want to characterize meridional transport because it leads to jets, and these jets seem to strongly suppress meridional transport. So what I'm showing here is, again, the dimensionless diffusivity, and now I have a new parameter on the x-axis, which is this dimensionless beta. So this beta star, which is beta made dimensionless using Rossby deformation radius and the base flow, when beta star is close to 0, so on the left region here, I'm back to the problem I showed you before. This is beta equals 0, the vortex gas scaling regime. And now as I increase beta from 0, so each one of these curves is a given value of the quadratic drag coefficient. We understand the leftmost value here on each one of these curves. This is the previous theory. And now I'm increasing beta when I move to the right. And you can see that when I increase beta, D star is going to drop by orders of magnitude, which means that indeed we need to include beta if we want to get the right value for this diffusivity D star. Now, how can we understand the impact of beta on the heat transport? Well, one simple idea is to ask that question: what is the energy containing wave number or the integral scale in that system at which the inverse energy cascade is going to stop? Okay, so the barotropic flow, which is this vertically average flow, it's obeying an inverse energy cascade, which leads to an energy containing wave number, which is well captured by the ratio of the root mean square velocity by the root mean square stream function. Now, without beta, in the first part of the talk, there is a frictional arrest mechanism. Bottom drag is going to stop the inverse cascade. This will lead to a scale which is comparable to the mixing length, which is also this intervortex distance. But if you compute it accurately like that, in fact, you get a log correction. So it's 1 over L times this log correction. But now, as I've told you, if beta is large, then instead of this frictional arrest mechanism, what the flow is going to do is that it's going to channel the energy into zonal jets that are separated by this Rhines scale. And if that's the case, then the energy containing wave number in the system should be the Rhines scale, which is root of beta divided by the root mean square velocity. So here is what happens. If I start from beta equals 0, or very low value of beta, the inverse cascade is arrested by the frictional mechanism. And the flow doesn't even reach the very large scales at which beta plays a role. So the flow will not feel beta. As I increase beta, the Rhines scale decreases until it becomes comparable to that frictional arrest scale. And that's when the flow is going to feel beta. So if I want to understand the control parameter in this system, I have to make the ratio of this estimate over this estimate. And that's when this ratio is of the order of 1, that beta should play a role. Okay, if I increase beta from 0, I can further replace this U squared with the estimate from the vortex gas dynamics. So here is the control parameter that I get. It's proportional to beta star. That's the only dependence in beta star. And then all these guys here are values when beta star equals 0, which means these are functions of the drag coefficient, either linear drag or quadratic drag. This is just linear in beta star. So I'm predicting that beta should affect meridional transport when this B becomes of the order of 1. So you can test that, and this is all the data you've seen before, but now I'm showing this diffusivity divided by its vortex gas value, the value for beta star equals 0, that's from the first part of the talk, so the curves will start at 1. And that's as a function of this parameter b. And you can see that this representation leads to an excellent collapse of the various curves onto a single master curve. You can go further than that and try to understand this limiting scaling behavior here for large B. And following Rines or Laroucheff and Held, you can say, well, when beta is really the dominant mechanism and this zonostrophic mechanism is channeling the energy into zonal jets, well, then maybe I can just forget about friction, since the friction mechanism is not playing a role anymore. So if you ask for friction to not play a role in this limit, you get an approximate scaling law, approximate because you have log terms here, where d star should be beta star to the minus 3.64. Turns out to be very close to, what is it? 40/11, I think. Okay, so that's the prediction if you ask for d star to become independent of friction in that limit. And indeed, this is the behavior you observe. It's in good agreement, and it's in good agreement for quadratic drag, like I'm showing you here, but also for linear drag, and I'm not showing the data here. So now we know that limiting behavior here, this is the vortex gas dynamics, and we know that limiting behavior here, which is this exponent here. So we can match the two and augment the scaling theory by simply matching these two limiting behaviors. If you do that, the only fitting parameters, the only new one is this 4.2 here, the exponent, the value and stuff. So, and I only need this 4.2 to explain the data over the entire range of linear drag, quadratic drag, and beta. Okay, provided the range where the flow remains fully turbulent. So that's nice. I have now included beta in the scaling theory, and I can play the same game and ask the same question. Is it doing a good job as a parameterization? So I'm going back to the system that's driven inhomogeneously by an imposed heat flux. Okay, so you can see again the temperature here and the barotropic kinetic energy. That's when beta equals 0. So that's the situation I've shown you before. And you can see that you have warm fluid here, cold fluid here. And now if I increase beta, you can see that, well, maybe you can guess that in the barotropic kinetic energy, I'm starting to see some jet-like features. If I increase beta further, I can see some well-developed zonal jets here in the system. And now I can zonally average these temperature fields and ask the question, is the parameterization, is the scaling theory a good parameterization to compute the theoretical profile? And the answer is yes. You can see for the 3 cases, the DNS profiles are in blue, and the predictions using the augmented scaling theory, this is the dashed line here. So in that case, the profile is some hypergeometric function, but that's not important. The point is that it's right onto the DNS, both in terms of amplitude here and of the shape of the profile. Okay, so this is the conclusion of the second part. I've shown you that including beta changes quite dramatically the structure of the flow. It reduces strongly the eddy diffusivity. And we came up with a quite naive, really, argument to augment the scaling theory, which is just, well, instead of the frictional mechanism, if beta is large, the flow is going to channel the energy into zonal jets up to the point where friction will not even have to play a role anymore. And that led to a good rescaling of the data and an augmented scaling theory that can be used as a quantitative parameterization here. Okay, so that's the end of the second part. And I'll just end with a few perspectives. Of course, you may wonder, these 2D models are nice, but, surely real flows are more complicated. And, the goal now is to include as many ingredients as possible to move towards a useful parameterization for a 3D climate model. And so we're now trying to include 3-dimensionality, which means that you're moving from the 2-layer QG model to a 3D ED problem, because it was introduced by ED during his PhD, with many people working on that problem. And the idea now is that you have a 3D flow. So instead of 2 layers, you have a uniform shear in the vertical direction. So the zonal flow now is sheared in the vertical direction with a uniform shear S. Then you have a strong vertical stratification, just like you had in the 2-layer problem, but it was just a difference in density between the 2 layers. Now it's a uniform continuous stratification. And on top of that, in thermal wind balance with this uniform shear, you have a uniform meridional temperature gradient here in the meridional north-south coordinate y. Okay, you have bottom friction at the bottom. And again, this system is going to be subject to the baroclinic instability, it's going to lead to turbulence, and you'd like to understand how much heat it's going to transport. So to answer that question, Ben Mikkel, who's a postdoc working with me, has developed a spectral solver called Coral. He's adapted it actually to the eddy problem. And here you can see a snapshot from what he's done, where you can see the total buoyancy, meaning the perturbation that has periodic boundary condition in the horizontal plus the background state. You can see that indeed it's warmer here than here. Maybe you can guess that there is a slope here in the isotherms in the system. And you can run very many of those simulations, changing the bottom drag coefficient. You can change the vertical stratification, you can change the shear here, and you're asking the question, what is the resulting heat flux, and can that be described by the two-layer QG theory that I've shown before? And the answer is yes. This is very preliminary results, but if you show the diffusivity as a function of the drag coefficient, the two being made dimensionless using the parameters of a quasi-geostrophic system, meaning the Rossby deformation radius and the velocity difference between top and bottom, well, you get that, I can show you other parameter values, but the very many values of stratification, of shear, of rotation rates, etc., that collapse onto a single master curve. And this black curve is exactly the exponential form, exponential 1 over kappa star, constant over kappa star, that you get from the two-layer quasi-geostrophic model. So that's really good news. It means that the phenomenology that we got from the two-layer quasi-geostrophic model carries over to the 3D case. So it has skill of describing more complicated situations. Okay, I thank you very much. I'll stop here. There's one paper out. And if you're interested in this Climate Modeling Alliance, you can read more on the website here. And I'll take any questions. Thank you very much.
Thank you very much. That was a very interesting talk, Bazil. Thank you. I had a couple of questions. The simplest one is back to the kinetic gas theory. You talked about the dipoles of positive and negative vortices transporting the temperature. That assumes that the positive vortex is not captured by a neighboring positive vortex, and that just swirl around without transporting anything meridionally. How can you be sure that the coupling is always heterosexual, so to say? And so that was one question. And then the other question I had was, if you think about the ocean, and you're not thinking only about the Southern Ocean, which is similar in some ways to the atmosphere, the models of zonal flows are really not appropriate. And not clear to me that the heat transport in the ocean can be explained in the same way. So those are such a good talk that I have lots of questions, but I'll stop at those two. Thank you.
Okay, thank you very much. Thanks for your questions. And of course, you know the ocean better than I do. So, I say that they're really good questions. Maybe I could start with the Southern Ocean. Part of the reason I focused on the Southern Ocean is that indeed, this is where that picture holds. And I believe it's also the case that this process in the Southern Ocean might be setting then the abyssal stratification, maybe throughout the global ocean. So you're probably right that maybe this is not the parameterization we should use throughout the entire ocean, as far as I understand. But if we're able to capture these processes in the Southern Ocean, I would be really happy already, I guess, as that question. Then considering the two vortices with the same sign that would rotate around each other, this is very much something that we see. And in fact, I think in the movie that I've shown, you can see pairs of vortices. And of course, all these vortex gas also include some merging events, and some new vortices formed. So I guess you do have all kinds of pairings, but only the pairings with opposite sign vortices will transport heat efficiently. I believe that, well, I could check, but I believe that if you just consider a couple of vortices that are spinning one around the other, I'm not sure that this is going to transport much heat, but
Yeah.
maybe I should double check.
Hi, Basil. Thank you very much. Very nice talk, and gives us hope in these trying times to see a positive result that explains something and is rational. I had just a couple of very simple questions. One is you introduced this parameter capital B to delineate the friction dominated from the beta dominated regime. I'm just wondering whether there is a simple estimate for what that capital B is in the atmosphere of the ocean or in a zone of interest, where in that regime you actually think we're likely to end up in. And the other question is, it's kind of reminded me, I mean, probably a wrong memory about this kind of old Heaton model by Stommel and others, right? It's kind of slightly off-centered vortices that also managed to propagate in a fashion, and I don't know whether it has ever been pushed to the point where it made predictions like your model did, but do you think there's any connection between that old model and you now? I mean, I understand you're doing a barotropic, you sort of have this interesting interplay between barotropic vortices and baroclinic advected quantities, which makes it kind of work. So I know the Heaton model was different, but do you think there's any connection between that?
Okay. Yeah, these are excellent questions as well. I've looked at Heaton's indeed, and in fact, there's been a bit of a debate on whether the dominant process is what I've shown, which is temperature anomalies being built between vortices, or whether the heat transport would be due to vortices just wandering around carrying their initial core temperature, which would be similar to what you're describing. And in fact, well, as far as we understand, in the limit of low drag, and you may argue whether it's the relevant one for the ocean, but we do find that the temperature that arises in between the vortices, that is considering a dipole of vortices, leads to much more heat transport than a single vortex, even a moving isolated vortex. But I think Thompson and Young, for instance, argued that there was also significant heat transport inside the vortices. I think it's just, it becomes subdominant in the limit of low drag. So that's one question. Then considering the value of B for the ocean and the atmosphere, maybe I should have said first that this theory is useful for the ocean much more than the atmosphere. The reason being that the Rossby deformation radius in the atmosphere is very large, it's thousands of kilometers, which means that it's going to be resolved by the climate model. So these structures we can resolve in the atmosphere, and we don't need a parameterization. The consequence of that also is that there is not much scale separation between the vortex size, the intervortex distance, and the size of the planet in the atmosphere, which means it is unlikely that I'm going to use that closure, because the very reason for the success of the diffusive closure that I've shown is some kind of scale separation between the radius of the planet and the intervortex distance in the system. Then for that reason, I haven't computed the value of B in the atmosphere. When I used values that seemed plausible for the ocean, I found pretty much what I showed, like that was within the range of what I showed. But of course, there is a huge unknown here, which is what are you supposed to use for the drag coefficient? Because whether it's that the linear, the Ekman friction on the flat boundary is not what you want to use for the ocean, and if it's quadratic bottom drag, then well, what value should we use? It's not quite obvious to make the connection to the turbulent boundary layer processes. That it'd be a great connection, but there's still work to do here. Starting with the barotropic flow, the reason I'm using the barotropic flow is because it contains the vast majority of the kinetic energy of the flow. Like it's, I don't know, like a significant fraction, most of it. So in fact, you can really think about that flow as just this vertically uniform vortex, in which case it's really a solution to a 2D Navier-Stokes equation, and you don't have that shielding. So I guess the answer would be these vortices, they don't have much vertical structure, in which case you're back to a 2D Navier-Stokes equation and you don't have that shielding. Considering Ekman drag, Well, that's pretty much what I'm trying to do when I use linear friction, right? So I have a linear friction coefficient, which could be the result of some Ekman drag. So I could do the boundary layer analysis and compute the friction and the pumping, etc. And I would get the value of that linear drag coefficient. Might be useful if I want to compare that to a laboratory experiment or some DNS where I really have nu and the flat boundary. But I think no one believes that these analytical result of the Ekman boundary layer holds, as a true quantitative model of what happens at the bottom of the atmosphere or the ocean. So instead of that, people have used linear bottom drag, picking the value of the coefficient to try to reproduce things they believe look like what we expect. So yeah, using Ekman drag would be a particular case, a particular value to the coefficient I've given. So in the data I've shown you, there were, I was changing beta, and there were several curves with various colors, which correspond to a given value of the quadratic drag. And I have similar data for linear drag. So on these curves, when I change beta, I do not change the value of the bottom drag coefficient, which is the main dissipation term. Concerning the hyperviscosity, which I haven't discussed very much, the idea is just that for any set of parameter values, I make sure that the hyperviscosity is low enough that it does not play any role. So, I divide it by 2, I check that it doesn't change the value of the meridional heat flux. So for any of the numerical simulations I've shown, I've made sure that the hyperviscosity is completely negligible in the power interval. Thanks for your question.